Introduction to Thermodynamics, Lecture 22. So we're transitioning away from talking about gases and talking about more of the energy that happens in a chemical reaction. So this is the first chapter of a couple that talk about what we call thermochemistry, the study of heat change in a chemical reaction. And so we're following now the energy involved. In addition to following what happens to the chemicals, now we're going to talk about what happens in terms of energy. So the first thing we have to sort of put into context is what we call the system. Right? The system itself is the whatever specific part of the entire universe that we're interested in studying. Right? So we're observing a system. Everything else in the entire universe we're called the surroundings. So a lot of this movement of energy is going to be between the system and the surroundings. So our system's whatever we're interested in. Everything else in the entire universe is the surroundings. So here we have three different examples. We have what we call an open system, where we're allowed to transfer mass and energy into that system. We have a closed system where we're only able to transfer energy. And then we have an isolated system where it's completely cut off and isolated from the surroundings. So nothing actually transmits through the system. For the most part, what we're going to be considering is this closed system where we're only transferring heat. Right? In some cases, we'll talk about changing mass, but for the start off, we're just talking about this closed system where we're only changing the heat. Right? So, or energy, excuse me. So when we talk about energy changes in chemical reactions, there's two different things typically we can talk about. We can talk about transferring heat, or we can talk about doing some work. Right? So let's talk about those individually. And we're going to treat them sort of in this lecture and the next individually. So in heat, it's the transfer of thermal energy between two bodies of different temperature. Right? So we're transferring energy, this heat energy, it's thermal, and between something that has thermal energy to something that has less thermal energy. And the way we're measuring this thermal energy is through temperature. But please keep in mind that the temperature does not equal the thermal energy. It's a measurement of. So when we transfer heat, we're seeing that transfer as a function of temperature. It's not directly related, but they're not the same. They're not equal. Right? The other thing that we can do is work. And this is transferring a force through a distance. In both of these cases, though, we're talking about the changing energy. So this bottom equation down here, we're talking about the change in energy is going to be the energy of the final state minus the energy of the initial state. So this delta or change is always the final minus the initial. Because there's two different things we can do with energy, then this change in energy is going to be equal to the amount of thermal heat that's transferred, Q, plus the amount of work done, W. So we're going to then relate this total energy to transfer of heat and amount of work done. Right. So let's look at those sort of individually. So here are two examples where the one we are doing just transferring thermal energy, this Q. In this case, where the heat is as we take the hot water from boiling down to cool it down at room temperature, we see that we lose temperature, so we're losing thermal heat from this system, this water, and it's going out into the surroundings. We could do something very similar where we bring heat in from the surroundings and cause that temperature to heat up. We're only showing one here. Right? So this means the heat is leaving the system, so our Q would be a negative number. Right? The second example here is we're doing some work. So we're increasing the pressure, so we're changing the volume of the system. Right? So the system is pushing back on this piston as we push it in. Right? So we're changing the volume. We are doing work on that system. Right? So going from one to the other, we are absorbing. Work is being done by the system to push that work is done on the system, so the pressure is increasing. Right? So W is going to be greater than 1. Right? So we can do either way. Right? We can have work done on the system or work done by the system, or we can have heat absorbed by the system or emitted or released from the system. These two can go either way, and they have a corresponding sign, right? So we can see how that's going to affect the signs of these two, work and heat, can be related to the change in energy in this table here, 6.1. One thing, the special thing about some of these quantities, this energy, for example, is that it consists of what we call a state function. It only depends on the state of the system. Right? So if we're talking about the change in energy, we're talking about whatever we're defining as the final conditions minus the initial conditions. It doesn't matter how we move from those initial state to the final state, just the fact that they are there is what we call a state function. It's only determined by the conditions of the system, not how those conditions are achieved. So if we look here at this example, we have two paths up this mountain. Regardless of how the hiker gets up to the top of the mountain, the energy they have, the potential energy of both of those hikers at the top is going to be the same, whether they took the straight forward path or the more meandering path. Right? Their potential energy at the top is going to be the same. So we can talk about energy being a state function, along with a value we'll call enthalpy. We'll talk later. Pressure, volume, temperature are all state functions. Entropy, again, we'll talk about that a little bit later, what that is, but all of these are state functions. It only depends on the conditions of where we started and the conditions of where we end, not necessarily how we go to them. All right? So one thing you'll see is work definitely is not on this list. So we can have some things that are state functions and some things that aren't state functions. All right? So let's look at this work then. So this delta energy is Q plus W. The most common work that we do in chemistry is this PV work, right? We're changing the volume because of pressure. So we can see here that this work is going to be equal to negative pressure times the change in volume. Right? That's how we're going to define work. So if we can we can then follow the amount of work done by monitoring the volume of this system. We also going to introduce ourselves to this new term. This enthalpy is defined as the energy plus the PQ, right? So that this enthalpy can be related to the amount of heat that's existed. We'll talk more about what enthalpy is a little bit later, but right now it's sort of we can stand it in, or it's equivalent or approximately equal to, if the volume doesn't change, the amount of the change in energy. So we can then sort of relate this enthalpy to the amount of energy that's transferred. And this allows us to do two different types of reactions. We can have what we call a exothermic process. It's a process that the system gives off heat or energy into the surroundings, or an endothermic process where the system is absorbing heat from the surroundings. Here's two examples of chemical reactions that are exothermic, and then again two that are endothermic. And we see, since the system itself is our frame of reference, if we're losing heat, that is going to be a product. Right? If we have to gain heat in, that has to be a reactant. So in an exothermic process, our heat or energy or enthalpy is going to be a product, right? And it's going to be negative. It's going to go out of the system. In an endothermic reaction, heat is a reactant. It's going to be positive because it's coming into the system. Right? So this the sign is a direct relationship of what is happening within the system itself. Right? So let's look back at this enthalpy. It's used to quantify the amount of heat that flows in and out of a system. And again, if we can follow the change in enthalpy as being the amount of enthalpy that's there at the final or in the product state minus the amount of enthalpy that's there in the reactant state. Right? So here we have two pictures. Right? If our initial process we have low enthalpy, and we go to these gases H2 and O2, we see that we have to, I said that backwards. So if we take H2 and O2 gases have a certain enthalpy, bring them together to form water, that enthalpy comes down. That means that that energy is lost. That's an exothermic reaction. Right? We can take, for this mercury oxide, decompose it, that takes energy in. That means our energy has to go up. That is an endothermic process. So again, as we see, we can relate this to the state at which we are, whether the products are compared to the reactants, but also the sign of this enthalpy value. If it's negative, that's an endothermic or exothermic reaction. Negative, exothermic. If it's positive, that is an endothermic reaction, because we're looking in reference to this system.
I don't get it.